Hello everyone. So in this video, I'll be introducing you people to a basic level task in machine learning. Particularly, I'll be using an artificial neural network to detect if a tumor is cancerous or not cancerous. The dataset comes from Kaggle. You can find it using this URL. It's basically a tabular dataset where you have some tabular features of the tumor, and then there's the target column where it is given that if that particular tumor is cancerous or non-cancerous. So M being the malignant and B being a benign tumor. The code for this task is already available on my GitHub. You can find my GitHub here, and then there are lots of projects where you can just simply explore them. I'll be particularly um, talking about this classification task. But you can also explore some of the other projects that I've done, and I'm planning also to make some future videos on them as well. Anyways, so I would not be going too deeper into the mathematical parts of it. My goal here is just to show people how to code a neural network and how you can use it to solve just a typical problem. So let's just begin. So the first thing is to import the libraries that we'll be using. Now I have imported some of them here, but then as we proceed to the code, I've also imported multiple tools that are suitable for conducting that particular task. So the first thing is to load the pandas library, which is used to import to load tabular datasets. Panda is a really handy tool which you can use to manipulate, load, and perform various operations on tabular datasets. Here we'll be using it to load our dataset. So using a CSV method, we can just simply import our dataset by passing in the path of the CSV file, and then we have it here in the pandas data frame. You can have a look at your dataset by printing the first few values or doing df.head. As you can see, we have these first 5 rows of the dataset printed. The next thing is to look for any inconsistencies in the data. Now, real-world data sets are really messy. There are lots of missing values, outliers, and other inconsistencies. So the first thing that a data scientist or ML engineer do is that they clean the data set. Now, this data set is clean already. There's not much that we need to do here as far as cleaning is concerned. But that's something that you would usually encounter solving any of the general level tasks. So here's this unnamed 32 column that was introduced to this dataset. I don't know from where, but I just have to drop it from the data frame because it's not useful to us in any way. So I just simply drop that column, and then the next step is to encode this diagnosis column. As you can see, rest of the features here are numbers, but this diagnosis column is a text. It's a character. Machine learning algorithms, on the other hand, they expect numbers because they're mathematical tools, and you cannot just simply pass the characters or strings. So for that reason, we have to encode this column into numbers. Now we have tools already available to us, which we can use to encode these um, string entries. Particularly, we'll be using the label encoder, which is there in the scikit-learn library. We just simply have to import the preprocessing tool, and then in the preprocessing, this is the label encoder that I imported, and I can just simply use its fit transform method to transform this diagnosis column, where now each of the characters would be assigned an integer number, and then we can use that for our machine learning analysis. Next step is then to separate the features from the labels. Label is the target column, which is what we need to predict, and features are the ones which we are going to use in order to predict the target variable. So features are stored in X, and the target variable is stored in Y. The next step is then to split this dataset into two sets. The reason for doing this is because when we have a machine learning model, the first thing is to train that model, and then we also need to see how well that algorithm performs. And for that reason, we set aside a small chunk of the data, which we then use in the testing phase to see how the model is performing. So we again have a tool in the scikit-learn library, which we can use to split the data set. The tool is called train test split. We just simply import it and then pass in the x and the y's and provide it the size of the test set that we want to create. Here I'm going to set aside 20% of the data for testing set, so that's why I'm passing 0.2 here. Now, xtrain contains the features for the training set, and xtest contains the features for the test set. And similarly, ytrain contains the labels for the training set, and ytest contains the labels for the test set. Next thing is then to standardize the data. Now, standardization is an operation that is usually required in tabular data sets for the reason that if you look into this data set, some of the columns you'd see vary in the range of thousands and some of them vary just in decimal places. Now, that is problematic from the algorithm perspective because algorithms just crunch numbers and numbers that are higher the algorithm try to or tends to put more weight on those columns as compared to the ones which have lesser values or they vary between a lesser range. Now that's something that we don't want it to do because we want this algorithm to treat each of the column equally because each of them are important in their own way. So for that reason, we need to transform their ranges from thousands or from whatever higher level range to a common range. And for that reason, we do what is called standardization. So what the standardization process does that takes the value, subtracts the mean of the column from it, and then divides it with the standard deviation, which brings it to a range that is in common with the rest of the columns as well. Now we don't have to do that from scratch as well. We have scikit-learn where we can simply import the standard scalar and then passing in the x train, we train the scalar and then we can just simply use that scalar to transform our features so that we have normalized features. So as you can see here, we have transformed the the training features, and we have transformed the test set features. The next step is then to construct the model itself. Now, the model that I've constructed here is a very simple basic level model. And the API that I'm using for it is Keras. Now, Keras is a high-level API which is built on top of TensorFlow, which makes it easier for you to construct neural networks. And that's why I'm using that to construct this neural network. There's also another API of Keras, which is called the functional API, which provides you more customization abilities. But that's useful when you have to construct a neural network that is highly customized and you want to do something, you want to try something new. But here we just simply need to, we just want to construct a neural network with 2 hidden layers and with 32 neurons in each with the activation function of ReLU. And that's why we don't have to so it's a pretty generic model. And then we have our output layer. We just have single neuron and the activation function is sigmoid because this model would be predicting probabilities, which would be deciding, which we then would use to decide if a tumor is cancerous or not cancerous. The loss function that we're using is called binary cross entropy, and the optimizer that we're using is Adam, and the evaluation metric that we're using is accuracy. Now, quickly going with these concepts, really, like this is just really a high-level overview. All of them have their own mathematical details to them, why we use them, but I'll just spare that for another video. Here, you can just see that within a few lines of code using Keras, we can code a neural network. The next step is then to train this model. So training a model is really, really easy. You just have to pass it the training data, the validation or the test data, and the number of iterations you want to train this model. And by calling the .fit method, you can just simply train your neural network. Now, since this code is inside GitHub, that's why you don't see the training procedure like the step-by-step or the epoch-by-epoch result here. But I'll encourage you people to take this code and try it in your own Jupyter notebooks or in your Google Colab, and you can see where each of the training step is printed step by step when you can see for yourself how the model trains. Once the model is trained, we can just simply plot their learning curves. Learning curves are curves which we, like it could be the accuracy of the model step by step or epoch by epoch, or it could be the loss of the model plotted against epochs. So as you can see, the accuracy initially starts very low, but then it suddenly jumps because this data set is really simple, it's easy for the neural network to learn it. And for typical problems like general level problems, you won't see something that quickly jumps to 90% accuracy. It would be a more gradual learning. Um, Once the model is trained, the next step is then to evaluate its performance. So we also have tools in scikit-learn for that. Um, we particularly will be using the classification report and the confusion matrix in order to evaluate how the model is performing. So what the classification report does is that it prints you the precision, recall, if one scores. These are mathematical metrics that are used to assess the performance of a model. And then we have the accuracy matrix, which is also printed in the classification report. So once the model is trained, we can then just simply pass it the X test, which is the test set features. And by calling the model.predict method, it predicts for those features if the particular tumors are cancerous or not cancerous. Now, as I said, the model outputs probabilities and not labels. In order to convert those probabilities to labels, we can just simply put a threshold on it, and then we can decide what needs to be decided as cancerous, like how much probability after which certain probability should be cancerous and should not be cancerous. So the typical probabilities that is picked is zero point 0.5, which is the 50% threshold. You can also play with this threshold as well and see how it affects the output performance. But for now, I've just kept it at zero point 0.5. Once we have the labels, we can just simply pass the model predictions and the true labels, and then the classification report is going to tell us what is its precision recall and what if1 score. As you can see, the model is performing pretty good. It's 0.97 or 97% accuracy. That is a really high accuracy. But just like I told you, this is a really simple problem. The dataset is really easy to learn. That's why you see this high performance even just with a simple model. You see the models perform really good. The final evaluation matrix is the confusion matrix. This is also a very handy evaluation metric, which is used in classification tasks. So what the confusion matrix tells you about is you have the ground truths on the y-axis and the predictions of the model on the x-axis. So for instance, if we read this number, what it is saying is that there were 74 such examples which the model predicted to be benign, and they were truly benign. And then there were 3 such examples which the model predicted to be malignant, but they were benign. So these 3 are the misclassifications, or the model confused them to be malignant tumors while they were benign tumors. And you can simply read the rest of the 2 numbers in similar way. So this is a really high level overview of the task. In the future videos, I'll be trying to go deeper into these coding, like these methods that I've used in the coding, and also the mathematical backgrounds of each of the concepts that we have talked about here. So I'm hoping to see you people in the next session. Thanks.